Hi everyone, my name is Ege, and in this video I'll walk through my code for the assignment 3. And the goal for this code is to build a convolutional autoencoder that takes a low resolution 28 by 28 image of a cat or a dog and upscale it to at least 56 by 56. This assignment is slightly different than the classification because we're not predicting a category. We're just trying to predict the pixels. Okay, and let's talk about the data set. So this assignment was provided, for this assignment, the images were provided from a Google Drive link. And in that link, we have around 25,000 training images and 12,500 test images. I downloaded the archive directly into the Colab using the gdom command. You can see it here. Because the folder was zipped in like 7Z style, I had to unzip them. After I unzip all of them, it read all of the images, and you can see in here we have around 12,500 images for the test and 25,000 training images. For each image, I produce two versions. The 28 by 28 version becomes my input X, and the 56 by 56 version becomes my target Y. And both come from the same source image, and the only difference is they just resize differently. I chose grayscale over RGB because for two reasons. Because first, the instructions explicitly mention that grayscale yields better results for simple autoencoder. Second, it keeps the network small. With RGB, the output layer would need 3 times as many parameters, and the training problems become significantly harder because the network will also need to learn color corrections. And after processing, the arrays are normalized to the 0 to 1 range by dividing by 255 and reshaped to PyTorch channels first format. And I'll also save them as .mpy file, so I don't need to reprocess 25,000 images every time I restart the runtime. That was explicitly recommended in the instructions. Let me go to the convolution autoencoder class. The tutorial's denoising autoencoder is symmetric, and the encoder pulls the image down 3 times, and the decoder upsamples back up 3 times, so the output has the same resolution as the input 28 by 25 in and 28 by 28 out. But we want an upscaler, we want a bigger output than input. And the way I solve this is straightforward. The encoder has one more upsampling stage than the encoder has pooling stages. The encoder has 2 pooling stages, starting from 28 by 28, and one max pool takes us to 14 by 14, and the second max pool takes us to 7 by 7. And then the decoder has 3 upsampling stages. From 7, we upsample them to 14, then to 28, and one more time to 56. And that's final upsampling stages. The entire reason the output is larger than the input. If I removed it, I would have a plain reconstructor like in the tutorial. And the other thing I changed from the tutorial is the filter counts. The tutorial used 8 and 16 channels, which is fine for MNIST. The MNIST digits are just white strokes on a black background and very limited feature diversity, but cat and dog's photographs are much richer. That's fur texture, different poses, variable backgrounds, facial features. So I scale the filter counts up to 32, 64, and 128 channels, and the total model has about 185,000 trainable parameters. And each convolutional layer uses 3 by 3 kernels with padding equal to 1, which means they preserve spatial dimensions. Only the pooling and upsampling layers actually change the resolution, and the final layer ends with sigmoid activation, as you can see in here, which clamps the output pixels values to the 0 to 1 range, matching the scale of my targets. So let's go and talk through the training section. The training loop itself is almost identical to the ones in the tutorial's autoencoder section. For the loss function, I used binary cross entropy. It's a natural fit when the target values are bounded in 0 to 1 and the output has a sigmoid on it. For the optimizer, I used ADA delta, which is what the tutorial was using, and it requires no learning rate turning, which makes it safe default. I kept the batch size as a 128. I trained 20 epochs and I wrapped everything in TensorBoard summary writer so I could monitor loss curves during training. And let's go to the results section. And here the results on 3 test images. You can see the images in here. Let me go through input generated and the true input again generated and the truth. Let's go back to the code again. Each plot has 3 panels. The top is the 28 by 28 and the whole network gets to work with. The middle is the 56 by 56 output generated by my work, and the bottom is the ground truth 56 by 56 version, what a perfect upscaler will produce. You can see that the network has clearly learned something meaningful. The overall shape of the animals or its pose and the general contrast pattern, the layout of lights and dark regions, all of these matches the ground version, truth version. Dog stills look like a dog. A cat still looks like a cat. However, the generated images are noticeably softer than the ground truth. Edges are blurred. The edges are blurry, and the fine details like fur strands or whiskers are missing. This isn't related to the bug. It's a characteristic failure mode of autoencoder trained with a pixel-wise losses on super resolution tasks. I think to get sharper results, I need to change like adversional losses, perceptual losses based on features from a pre-trained network like VGG or residual connections that let the network learn only the high frequency correction on top of bilinear upsample. All of those are out of scope of this assignment. To sum up, I built a convolutional autoencoder with asymmetric encoder and decoder structure, where the decoder has one extra sampling stage relative to the encoder. I trained it on 25,000 grayscale cat and dog images with BCE loss and ADA delta for 20 epochs. The output is not pixel perfect, but it is recognizably faithful to the ground truth. The animal silhouette, pose, and the general structure are all preserved. Thank you for watching me, and this is the end of my homework